Probability of finding a particle in a region. What is the probability of finding a particle in a box of length capital L in the region between x equals capital L over 4 and x equals 3 capital L over 4 when the particle is in part A, the ground level, and part B, the first excited level? There is a hint: integrate absolute value of psi squared dx, where psi is normalized between L over 4 and 3L over 4, and part C are your results in parts A and B consistent with the figure. Explain. So for a particle in a box, as we have done in the lectures, we have found that the wave functions are given by a normalization factor, capital A, multiplied with sine of k sub n x. So n is our quantum number, and the boundary conditions are given by the wave function has to vanish at the boundaries. Psi n of 0 should equal to psi n of capital L, which is equal to 0. And this leads to the quantization of the wave vector k as n pi divided by capital L, and this n quantum number is an integer, 1, 2, 3, etc. Okay, and if we plot these wave functions, substituting n pi over L here, basically this is what we obtain as shown in the figure: n equals 1, n equals 2, n equals 3, etc. As you can see, the wave function does vanish at the boundaries. So this what is plotted here is not the wave function itself, but it's the square of the absolute value of the wave function. Therefore, this represents the probability density of finding the particle in a region between x and x plus dx. That's psi of x absolute square times dx is the probability density multiplied by dx. So the probability of finding the particle in a region between capital L over 4 and 3L over 4 is given by the area underneath the psi square curve for n equals 1 and n equals 2. So these two areas suggest that the probability will be higher for n is equal to 1. So let's see if that's the case. So first we look at the normalization condition. The normalization condition tells us that the probability of finding the particle between 0 and L, which is absolute value of psi square dx, this is the statement that says the particle exists in the box. This probability should be equal to 1, so it's a square sine square k sub n x dx. This must be equal to 1. So that's our normalization condition. And if we perform this integration, we find that a square integral from 0 to L. For sine square, we can substitute 1 minus cosine 2kx divided by 2 dx, as cosine 2kx is equal to 1 minus 2 sine square kx. This is going to give us, for this part of the integral of dx is x, evaluated between 0 and L, it is equal to L, so a square capital L over 2. And this part is going to turn into the sine function, which when evaluated between 0 and L at the limits, it's going to give us 0. This is equal to 1, and this tells us that the normalization constant is square root 2 over capital L. So that's what we find from the normalization condition. Therefore, I recall that the wave functions in its full form can be written as psi sub n of x is equal to square root 2 over L, capital L. This is our normalization condition. constant multiplied by sine n pi over L, capital L, x. So this is what we know because k is n pi over L, so that it satisfies the boundary conditions. Now, for part A, n is equal to 1. We have the ground level. So the wave function corresponding to the ground state is psi1 of x is equal to square root 2 over L, 2 over capital L, sine pi x over L. Okay, and let me just note here that here I have used cosine 2 theta is equal to 1 minus 2 sine squared theta identity, trigonometric identity. Okay, so what's the probability of finding the particle between x equals capital L over 4 and x equals 3 capital L over 4? So in this range. This is the integral from capital L over 4 to 3 capital L over 4, probability density dx, where the probability density function is absolute value of psi squared. So we can substitute for psi1 to calculate the probability. X between L over 4 and 3L over 4. This is equal to, when we take the square of this, we get 2 over L, 2 over capital L, integral capital L over 4 to 3 capital L over 4, sine square pi x over L dx. Okay, now I'm going to use this trigonometric identity again. So this is going to be 2 over L, 2 over capital L, integral capital L over 4 to 3 capital L over 4, 1 minus cosine 2 pi over capital L x dx. So absolute value of psi square 2 over L, 1 minus cosine 2 pi x over L dx. And remember that sine squared theta is 1 minus cosine 2 theta over 2. So we need also a factor of 2 here. So these 2's will cancel. Okay, and this will give us, for the first term, so we have 1 over capital L, the integral of dx is x, the integral of cosine 2 pi x over L is minus capital L over 2 pi, sine 2 pi x over L, and this is to be evaluated between x equals L over 4 and 3L over 4. So that's going to give us 1 over capital L. The difference between 3L over 4 and L over 4 here is going to give me L over 2, 2L over 4, which is L over 2. And then I have, when I substitute 3L over 4 here, this is going to give me 6 pi over 4, which is 3 3 pi over 2. And then I will have L over 4 substituted here. L over 4 will give me sine pi over 2. So I have sine 3 pi over 2 and sine pi over 2. The difference will give me a factor of minus 2, but because I have a minus sign, it's going to be plus. So this is plus L over 2 pi multiplied by 2. And if I calculate this number, that's going to be probability x is between L over 4 and 3 capital L over 4 is 1 over 2 plus 1 over pi. So my final answer to part A is then probability x is between L over 4 and 3L over 4 this number 1 over 2 plus 1 over pi gives us 0.818 as the final answer. Okay, so here I had 1 over 2 plus 1 over pi, as you can see. Alright, so let's move on to part B. Now we will repeat this calculation for the first excited state, for which n is equal to 2, psi 2 of x is given by square root 2 over L sine 2 pi x over L Now this probability is x between L over 4, 3L over 4 is the integral. Square root 2L squared will give me 2 over L, 2 over capital L. Now I have to integrate between L over 4 and 3L over 4. This time sine square 2 pi x over L dx. And I can use the same trigonometric identity again. This will give me 2 over L, 1 over 2, so integral from L over 4 to 3L over 4, 1 minus cosine 4 pi x over capital L dx. The 2's cancel again, and now I can evaluate this integral. This is going to be 1 over capital L x, so the integral of dx is x, and then I have capital L over 4 pi sine of 4 pi x. This is to be evaluated between L over 4 and 3L over 4. Now, when I put here L over 4, you can see I'm going to get sine pi. When I put 3L over 4, I'll get 3 pi, sine 3 pi, which are all 0. So this is going to give me 0. Therefore, I will find the probability for x between capital L over 4 and 3 capital L over 4 to be equal to no contribution from this side. This is L over 2 multiplied by 1 over L. So that's going to be 0.5. The answer is 1 over 2. Now, if I compare the result I found in part A with part B, I see that these results are consistent. with the figure. The red area corresponds to the ground level, and that area, according to this calculation, is 0.818, and the green area is 0.5. So if I look at these areas visually, I can see that this area is 0.5, this area is 0.818, so the results are consistent with the figure. So here I have calculated the probability of finding a particle in a box with length L in the region between L over 4 and 3L over 4. First in the ground level and second in the first excited state. The wave functions are given by a sine n pi x over L because they have to obey the boundary conditions, and the normalization constant is found by normalizing the wave function. The probability of finding the particle between x equals 0 and capital L is 1, which means the particle exists. So that gives me a is equal to square root 2 over L. Square root 2 over L sine pi x over L, psi 1. When I take the absolute square of this and integrate it from L over 4 to 3L over 4, I obtain 0.818. And for the first excited state, square root 2 over L sine 2 pi x over L parentheses squared, when integrated between L over 4 and 3L over 4, gives me 0.5, and that's consistent with the area underneath the psi absolute square curve between L over 4 and 3L over 4.